All right, welcome to section 10.5, which is the last section in the book. You have made it this far. Congratulations. 10.5 is how to use the regression slope to conduct theory-based inference. So in 10.4, we talked about using simulation-based inference for the regression slope. In this section, we're going to move on to the theory-based approach. And if you remember from every other chapter in this book, when we've done the theory-based approach, we've needed two things. We've needed theory-based validity conditions, and then we've needed some sort of way to get the standard error of our statistic, right? So, let's get through this relatively quickly, hopefully. The validity conditions that we have are the general pattern of the points should follow a linear trend, so you shouldn't see any sort of curved or nonlinear patterns. The regression line should have about the same number of points above and below, and by and large, if you divide the plot up into multiple chunks, you should still have the same number of points, give or take, above and below. So if you divide the plot up into thirds along x, you should, for each one of those thirds, still have symmetric distribution of points around the regression line, give or take. Okay, so things shouldn't be terribly lopsided. The third validity condition is that the variability of points around the regression line should be similar regardless of the value of x. And what that means is that we need equal variance all the way across the regression line. Okay, so the next few slides we're going to look at what these mean. The general pattern of points should be linear means that only the first plot is something that we could conduct theory-based inference on. In the second plot, we've got evidence of some curvature. In the third plot, we've got evidence of curvature. In the fourth plot, I don't know what we have. I mean, okay, it's a dinosaur, but there's no evidence of any sort of linearity there. It's not clear what we'd be conducting theory-based inference on. So, yeah, can't do theory-based inference on a dinosaur. Never thought I'd say that out loud. Okay. Second requirement is that we have symmetry around the regression line. So if your regression looks something like the picture on the right, where you have a few points that are way, way, way far down, then you've got clearly most of your points are above the regression line. The ones that are below the regression line are really far below the regression line. And so this assumption would be violated. This is an issue because one of our biggest assumptions, more formally, when we're writing this out, is that the errors, the residuals, are identically distributed with a mean of 0. And so when we have asymmetry like this, we don't have a nice symmetric distribution of errors. We don't necessarily have errors that have a mean of 0 for any given section of the line. It's just a problem. All right. So if you remember in chapter 6, we required that we either had symmetry or 20 observations plus not horrible asymmetry. In this case, we actually just require symmetry all the way around. Okay? The final requirement for theory-based inference is equal variance. So on the left, the points are about the same height above and below the regression line all the way through the line. On the right, though, we have a fan shape that kind of spreads out from our regression line, and that is indicative of what's technically called heteroskedasticity, which is a big word that means unequal variance. One way to think about this is if you divide your graph up into like 4 pieces that have approximately the same number of points, right? So divide it up into 4 equal pieces by number of points, not by x-axis length. Then draw lines for maximum and minimum point within each chunk. Those should be about the same length apart, right? So your max and min should be about the same length apart for each chunk of your graph, all right? That's one way to kind of check and test whether the assumption of equal variance or homoskedasticity holds, okay? Now, sometimes it can be kind of hard to tell whether the equal variance assumption holds, and that's not your fault. It's actually, this is another piece of research that I work in, is how people perceive graphs and how we can read information off of graphs. But what my research has shown is that when there's any sort of underlying change in the mean, we're not particularly good at assessing the vertical distance, which means that sometimes it's easier to look at the residuals than it is to look at the actual data. So our residuals should be symmetric around 0, that's the previous assumption, and should have about the same variance across the length of x, all right? So here that's obviously not true. Sometimes it's a little more subtle, but it's not uncommon to have situations where the variance increases with the mean of x or the mean of y. So that fan shape is something that we need to look for, and something that we need to not see to safely do theory-based inference. Okay. Now, the next thing that we need for any sort of theory-based inference is a formula for the standard error. So if we are doing inference on the correlation coefficient r, then the standard error formula is pretty easy. It's just the square root of 1 minus r squared divided by n minus 2. Okay, that's pretty straightforward. Then our t statistic is just r divided by the standard error. Now, t can be calculated from the slope as well as the correlation coefficient, but because they depend on the same data, the test results are going to be identical. So if we wanted to, we could take the standard error formula and we could also make some sort of confidence interval for the correlation coefficient using the standard error. We could make confidence intervals based on the slope if we had a standard error for the slope. Now, you could be sneaky and creative to get that, but it's probably easier just to get that from the table that is usually given from any sort of statistical software that is working with the regression. You can also get the table from the applet if you're using the applet. This is the regression table. You can get your standard error from there. All right, and just make sure you're getting the correct standard error by finding the row that has your explanatory variable there, and then skip past the coefficient, which is the estimate, and go for the standard error. All right, so the trick here is reading the correct number off the table. If you're already using the table, though, you may as well just grab the t-statistic and the corresponding p-value from the table. So that is another option. All right. So we've done our, we figured out how to get our standard error. We can take that standard error and calculate a t-statistic or steal it from the table. We can also make a theory-based confidence interval for the slope using that same standard error. And that would give us an plus or minus estimate, right, of what the population slope value is, which we can then interpret in the context of the problem as when x increases by 1, the average value of y increases by between lower bound, upper bound. Sometimes that's a useful thing to have, all right? So if we're interpreting things, we've got a hypothesis test. We say with t equals blank, I have some sort of strength evidence to suggest that there is a linear relationship between x and y. I either accept or reject the null hypothesis and conclude that something related to the context of the problem. If we created a confidence interval for the slope, then we say I am 95% confident that as x increases by 1 unit, the predicted population average value, need all of those words, right, of whatever y is, will change by between lower bound and upper bound of the interval, okay? So we need the predicted to say this is a y hat. The population average value is something that says, okay, we're talking about beta, right? So we're talking about the population version of this regression. And just as a reminder, we're predicting the mean. We're not predicting the value of any single observation, which means that we need to say average value, okay? So those words all matter, okay? So if we look at our head size and brain weight example, we can see that t has been calculated for us. It is 20.409. The p-value is 5.96 times 10 to the negative 54th. Okay, so basically 0. So we have extremely strong evidence that there is a relationship between head size and brain weight. We could make a 95% confidence interval for the slope, and you can get this out of the applet, of course, but the confidence interval is not going to match. So in this class, we use 2 times the standard error to get a confidence interval. So 0.263 plus or minus 2 times the standard error from the table, which is 0.0129, which means that we are 95% confident that the population average brain weight will increase by between 0.237 and 0.289 grams for each additional cubic centimeter of head size. All right. So that's not too terrible, I think. The nice thing is you don't have to compute the standard error for the slope yourself. You just have to find the right number. Okay. If we interpret things for the correlation coefficient, the basic interpretations don't change, in the confidence interval especially. We have to say I am 95% confident that the population correlation between x and y is between lower bound and upper bound. So that's really the only change. All right. And guys, I'd just like to offer my congratulations. You have listened to the last section-based lecture of this class. We made it.